Let's graph a couple more parametric curves just by plotting points. So let's start out with this one, 2t comma 3t. So this is another way to write the parametric equations, x equals 2t and y equals 3t. So we can plot this by just making a table with some t values and the corresponding x and y values. So when t is, say, -1, x is -2 and y is -3. When t is 0, x is 0 and y is 0. And when t is 1, x is 2 and y is 3. I chose these t values mostly because they're convenient. In principle, we could choose any t value to generate a point in the xy plane. So when we plot these, let's see, so -2 and -3 there, and 0, and then 2 and 3. And, you know, if we plotted lots of other points for different t values, it would trace out this line here. And it's tracing it out so that it's moving from the lower left to the upper right, because as t increases, our points are moving upwards and to the right. Okay, now let's try this other parametric curve. This is the parametric curve where x is 2 sine t and y is 3 sine t. So let's make a table for this one. Let me put our graph down here, and the table I'm going to try to fit in up here. So t, x, and y. Since the domain of these parametric equations is all real t values, I can choose whatever t values I want, so I'm going to choose nice t values. Since my t values are going to go into sine, let me try, how about -π/2? Then sine of -π/2 is -1 times 2 is -2. And then for y, we get -3. Then when t is 0, let me do actually -π/4. When t is -π/4, sine of that is -√2/2 times 2 is -√2. And then for y, we get, what, -3√2/2. And then let me jump up to 0. Sine of 0 is 0, so x and y are both 0 here. And then let me jump forward to plus π/2. Sine of π/2 is 1, so we get 2 and 3. Okay. So for these points, we get, let's see, -2 in the x direction, -3 in the y direction here, and then -√2, so that's about 1.4, and then -3√2/2, that's about 2.1 or something, so somewhere in here, and then 0, and then 2, 3, so up here. And because sine never gets bigger than 1 or smaller than -1, our graph never actually leaves the interval between these 2 points here. So it goes back and forth like this, up to the right, and then it turns around and comes back down to the left, and then once it reaches this bottom point, it goes back up and to the right. So something you might notice about these two graphs is these are actually the same line. Both of these parametric curves trace out the same graph on the xy plane, but they trace it out differently, right? This first parametric curve, it just goes up and to the right. And the second parametric curve, it kind of bobs back and forth like this, right? It keeps retracing the same ground, but it stays on this line, y equals, I guess it's 3/2 x, and it just bobs back and forth. So, you know, the one lesson to take from this example is that the parametric curve, a parametric curve, or a pair of parametric equations like this, it doesn't just describe a geometric shape in the plane. It also gives you a very specific way of tracing out that shape. So it traces out that shape in a particular direction, and at a certain speed, possibly with backtracking as we see here. So a parametric equation has a lot more information in it than just a shape, right? It's actually a particular way of tracing out that shape. So there's a lot of redundant, well, not redundant, there's a lot of information in here besides just the shape. If we want to extract the shape from this parametric equation, we can actually do that. Right? If we take these parametric equations, x is 2t and y is 3t, it might have occurred to you, well, we have 3 variables, but there are only 2 coordinates in the xy plane, so shouldn't we be able to eliminate one of these coordinates? And the answer is yes. Let's eliminate t, just because t doesn't correspond to one of the geometric coordinates in this picture. So to eliminate t, we can solve this first equation for t. So that's going to give us x over 2 equals t. And then we can put that into the second equation. We get y equals 3 times x over 2. So that's y equals 3/2 x. And you can see that we've eliminated the parameter here. T isn't in our equation anymore, and we're left with a single equation, and this equation is the equation of this line in the xy plane. So we've eliminated the parameter, and we got the xy equation for the curve. This xy equation for the curve, it no longer contains information about how we traced out this curve. It only describes what points are on the curve, not how they're traced out. Okay, let's try this trick with this other way of tracing out this line. So this one was x equals 2 sine t and y equals 3 sine t. So we can solve the first equation for x. That gives us x over 2 equals sine t. So then we need to take inverse sine, I guess. So inverse sine of x over 2 is t. And now we can plug that into the other equation. So y equals 3 times sine of inverse sine of x over 2, but sine of inverse sine of x over 2 is just x over 2, and we get y equals 3/2 x. So, eliminating a parameter like this actually does 2 things for us. First, it gives us an equation that we might be able to identify, right? At the beginning, maybe you didn't know what this parametric equation was actually tracing out, but when we convert it to a Cartesian equation with just x and y, it's, we have more experience with this kind of equation, and so we can identify more shapes, right? So eliminating the parameter sort of let us know what shape was being traced out here. The second thing that eliminating a parameter does for you is it allows you to directly compare 2 parametric curves. So, for both of these, even though these parametric curves, these 2 parameterizations of the curve, we're tracing out the curve differently, when we convert to Cartesian equations, they actually produce the same Cartesian equation, right? And what that tells us is these 2 parametric curves, they're different, but they aren't different because they're different curves. They're the same curve, but traced out differently. So that's the second thing that eliminating a parameter does for us. It lets us identify when 2 parametric curves are actually the same curve, but just traced differently. Let's look at one more example of eliminating a parameter. So let's identify what this parametric curve is by eliminating the parameter. So we have x equals t plus 4 is our first equation. And the second equation is y equals minus t squared minus t plus 2. So we can solve either equation for t, and it definitely looks like it's going to be easier to solve the x equation for t, because we can just subtract 4 from both sides. So x minus 4 is t. And then we can put that into the other equation, and we get y equals minus, So we're replacing t with x minus 4, so don't forget these parentheses, minus t, which is x minus 4, plus 2. So, looking at this, it's definitely going to be a parabola, but to identify which parabola, we're going to have to multiply this out. So negative x squared plus 8x minus 16. So I've multiplied out this squaring, and I've distributed that minus sign there. And then from this second term, minus x plus 4, and then the plus 2 at the end. So this is y equals negative x squared, and then plus 8x minus x, so that's plus 7x. And then minus 16 plus 4 is negative 12, plus 2 is negative 10. All right, so this is the parabola that's traced out by these parametric equations. Of course, having the equation for the parabola sort of destroys the information about how this parametric curve is tracing out the parabola. So this particular parabola, it looks like it's something like this. And just having this equation doesn't tell you which way this parametric curve traces. Does it go to the right or does it go to the left? To figure out that, you'd have to actually plug in a few t values, at least mentally, and see what's happening to the points that you get. So as we increase t, the x values get bigger, and that means that we must be moving, the parametric curve moves along this parabola rightwards, like this.